Welcome to CPU Science Unlocked, where we'll explore the ideas behind modern processors and why they matter. In this presentation, we'll touch on how processing power evolved, why transistor density and cache hierarchies are central, and how architectural choices shape performance and efficiency, giving you a high-level map of the technical themes we'll unpack together. This slide traces CPU evolution from early 4-bit designs to today's multi-core 64-bit chips, guided historically by Moore's law and exponential transistor growth. It shows how microarchitecture added pipelines, caches, and vector units to boost throughput, and highlights the practical constraints, physics, manufacturing, and power that designers juggle to sustain growth within real limits. Here we walk through the instruction cycle, the sequential engine that turns software into machine action. Instructions are fetched, decoded into control signals, executed as micro-operations, and finally written back to memory, while a control unit updates the program counter. This flow is the fundamental transformation engine that drives observable program behavior and user interaction. Instruction pipelining overlaps fetch, decode, execute, and write-back stages to increase throughput, but it also introduces hazards. Data dependencies are handled with forwarding and stalls, while branch hazards rely on prediction logic and speculative execution. The slide emphasizes the trade-offs between added complexity, power cost, and real-world performance gains when balancing optimization strategies. Caches exploit locality to bridge the huge speed gap between CPU cores and main memory with a multi-level hierarchy. Small, fast, private L1 caches, larger L2, and shared L3. Associative lookups enable fast hits while misses cascade down to lower levels, and the slide shows how improving hit rates dramatically reduces pipeline stalls and keeps execution units fed for higher utilization. Branch prediction and speculative execution are all about guessing the future to keep pipelines full. Prediction engines use history tables, simple patterns, or even neural predictors to forecast control flow, allowing instructions to be fetched and processed ahead of time. Correct predictions boost throughput, while mispredictions force costly pipeline flushes, so accuracy is central to modern CPU efficiency. Pushing raw frequency faces, diminishing returns because of reduced gate delay tolerance, rising dynamic power and heat, and even quantum tunneling at tiny scales. Designers must balance raw hertz with architectural improvements, wider pipelines and vector units, energy-efficient geometries, and optimized transistor designs, all aimed at squeezing more performance without unsustainable power or reliability trade-offs. The core scaling paradox shows that while adding cores multiplies theoretical throughput, system bottlenecks quickly erode real gains. Shared caches, coherent interconnects, and power budgets introduce diminishing returns unless software is parallelized to match hardware scaling. The imperative is clear. Hardware advances must align with algorithmic and programming improvements to deliver visible speed-ups to users. Deep UV and extreme UV lithography pushed density for decades but now approach silicon lattice limits, bringing variability, quantum effects, and soaring fab costs. This slide outlines alternative frontiers, novel materials like graphene or carbon nanotubes, 3D stacking and angstrom-scale nodes as potential paths to sustain historical density trends while acknowledging the practical challenges of that transition. Power density is the ultimate constraint on CPU ambition, forcing architectural responses like sophisticated throttling, workload adaptation, and new transistor geometries. The slide highlights FinFET and gate oxide improvements, dark silicon strategies that selectively power regions, and future frontiers such as 3D integration and materials research, all aimed at managing power while preserving performance and reliability. The evolution to heterogeneous computing shows how general-purpose CPUs are being augmented with specialized units, AI matrix engines, cryptographic accelerators, and vector units to merge flexibility with throughput. The slide foreshadows adaptive instruction sets that analyze workloads and tailor execution, pointing toward processors that adapt hardware resources to specific tasks rather than forcing every workload through a single general-purpose core. Looking beyond CMOS, emerging devices promise new computational models. Carbon nanotube transistors offer nanoscale mobility and energy efficiency. Spintronic logic uses electron spin for low-E power, non-volatile computation, and quantum tunneling devices exploit atomic-scale phenomena for ultra-fast switching. Each approach could lower voltage and increase speed, with research aiming for practical implementations in the coming decade.